Okay, so our last lecture we started talking about Rn. We focused on linear transformations. We did kind of a little review of linear algebra. Today we are going to maybe even take a step back from that and think about normed vector spaces in general. And the reason I want to do this is, Tao sort of did this very early on in the first chapter, and we sort of rushed through it. So in particular, like at the end of this lecture, we're going to talk a lot more about Cauchy-Schwarz than we did back at the beginning of this semester. Okay, and the other reason is this is just kind of setting the stage for all of our analysis in Rn, which again is what we're going to be doing for the rest of the course. Okay, so we've got today's lecture on just normed vector spaces in general, and then we're going to have Monday's lecture on norms of Rn. Okay, so we'll be specializing this stuff on Monday. Okay. Okay, so there are vector spaces, and we know that. I just want to remind you of a few, just to keep in mind here. We have Rn, okay, but we also have, say, polynomials in one variable. Or, we can make a bunch of them. Let's say continuous functions that map from the closed interval 0, 1 to the reals. Okay, that's three different ones to keep in mind throughout today's lecture. Okay, so again, we're being a little bit more general than Rn. Okay, you can check that those are vector spaces. Because we can add two vectors there. We also have scalar multiplication. Our scalars in all three cases come from the real numbers. Okay. Now, a definition that I don't think you see in linear algebra is the next one. It's the definition of a norm on a vector space. Okay, so a norm is going to be a thing we associate to a vector space. Now, normally, let's say we've got a function f of x. We'll say something like f maps 0, 1 to the reals, say, to define the function. The problem is that we want to actually denote the norm by double vertical lines. Okay, so now if our norm is going to be denoted double vertical lines around x, okay, that's like our version of f of x, well then what's the version of the second thing where we say what it maps from and to? Okay. So what we do, this is notation that, it's standard notation. I don't think we've done it in this course. So if you've got a function that isn't in standard function notation, the convention is you just put a dot where the variable would go. So here this is double vertical line with a dot in there. That's the function that maps, that's the norm, and the norm maps from the vector space to the reals, and it has to satisfy some axioms. Okay. It has to be non-negative. It's equal to 0 only for the 0 vector. So here, we didn't go through the vector space axioms, and we're not going to. I just want to recall that every vector space has a unique 0. Okay, and we'll just be denoting that 0 vector as 0. Okay. Third rule. If you multiply the vector x by the scalar c, the norm of that will be the absolute value of c times the norm of x. Okay. Just want to make 2 comments here. The first is that is absolute value. Okay. The second is that we've said this is true for real scalars, and we said up here our vector space is a vector space over the reals. So that means that our scalars are real numbers. So, okay. And the fourth one. The norm of x plus y is at most the norm of x plus the norm of y. Okay, are there any questions on norms of vector spaces?
So this sort of works like a metric, but only from 0. Like you're always evaluating your metric compared to 0.
Right, yeah. So a norm is giving you, in some sense, a distance from 0, okay? But since it's a distance from 0, we usually would think about it as the norm is giving you a magnitude, okay, or a size. Okay. So, if our vector space is just the real numbers, then the obvious norm is just absolute value. Okay? Because absolute value gives us size. Okay? Any other questions on norms before we move on? Okay, I have one. What does this fourth property remind you of?
Triangle inequality.
Yeah, it is the triangle inequality. So if we drew a picture of it, okay, well, the picture of a vector space, the vector space we can actually visualize is the plane, okay? And then we draw 2 vectors. Let's draw an x and a y. And now we have this parallelogram rule for how we add vectors. So our vector x plus y is that one. Okay. And now the fourth axiom for norms is telling us that the length of the vector x plus y is at most the length of the vector x plus the length of the vector y. Okay, so that's in this setting telling us the length of the hypotenuse is at most the sum of the lengths of the sides. Okay. We mentioned a couple examples. I'll give you a couple more. Let's just stick we'll just stick to Rn. Okay, we'll define, we've defined all of these as metrics early on in the semester. Now we're going to define them as norms. Okay, so the one norm is defined by the one norm of the vector x, where x is a vector in Rn, is the sum of the absolute values. The two norm is the square root of the sum of the squares. Okay. The infinity norm is the maximum absolute value of a component. Okay, so those are all, oops, got a little carried away here. There's no infinity in there. That's just the infinity norm. Okay, 3 examples of norms. We could define the p norm actually. Okay. And then you'd see that actually the 1 and the 2 norm are special cases of the p norm. And indeed, the infinity norm is what you get when you take the limit as p goes to infinity of the p norm. Okay, but that's sort of beside the point for today. Okay.
Dr. Bader?
Yeah.
Do we keep the properties we proved about these as metrics where we have the, they have the relation between them? I forget exactly how it goes. So we showed convergence in one metric is convergent in the rest. Do we retain those types of relations?
Yeah, so what we're going to do is this lecture and the next lecture, we're basically redoing that. I wasn't very happy with how we did it before. So we're doing more in this lecture and the next lecture, and in particular, we're going to redo all of that. So it's still true, and we'll see another proof of it.
Okay, I'll pretend I don't know it's true yet.
No, it's okay. It's okay. We're going to see better proofs, I think. Okay, now, how do norms and metrics compare?
Well, You can define a norm by taking a metric and a vector to zero. So if you have a metric, you can make a norm.
That's tempting to think, right?
Yeah.
How are you gonna satisfy that one? Property 3 of a norm. Yeah.
Almost.
Right.
No.
So, if you have a special metric, you can use it to define a norm. But it would have to be a special metric that satisfies the scalar condition. Okay? What about the other direction? How would you get a metric from a norm?
You can do a absolute value of the difference of the norms. Something like that.
You can just divide it to be the norm of the difference.
Mm-hmm.
I don't know the difference.
So Daniel's suggestion is interesting. I don't know if that works. If anyone has some free time, that'd be interesting to check if Daniel's suggestion works about taking the absolute value of the difference in norms. But the easier way is just to define the metric. And let me say, if that works, it's different than the normal way. So the normal and easy way is to define the metric to be the norm of the difference of the vectors. So our proposition is just going to say that is indeed a metric. So if you get a norm on the vector space V, then the function d of xy defined to be the norm of x minus y is a metric on V. Okay, now you just have to remember back to the axioms of a metric. Anyone remember them?
So we have positivity or non-negativity.
Uh-huh.
The metric equals 0 if and only if both both points are the same.
Yep.
Triangle inequality.
Yeah.
And symmetry.
Yep.
From the chat, I took the last two from the chat.
Yes, thank you, Roger, from the chat. Okay, so I think the metric is 0 if and only if the 2 points are the same. That's coming straight out of property 2. Positivity / non-negativity, that's coming straight out of property number 1 of a norm. What about symmetry? Where do we get symmetry?
From number 3.
Yeah, symmetry is scalar multiplication by -1 because we have this. Okay. So we get symmetry out of scalar multiplication by -1, and we just have to, that leaves us with the triangle inequality. Let's write out a proof of the triangle inequality. For all of these things, that's usually the only one that's not obvious. Okay. So let's take x, y, and z in our vector space. Let's look at the distance between x and z. By definition, that's the norm of their difference. Now we can do our standard thing, where we add and subtract a y in there, because our goal is to introduce the y into the metric. Let me get the lights back on. There we are. So we will do that. And now we can use the triangle inequality of the norm. There you go. So that gives us the triangle inequality for this metric. And we'd already checked the other properties. Any questions there? So, if we have a normed vector space and we don't say, okay, so if we have a normed vector space and we're looking at it as a metric space, if we don't say that anything different, then the metric is this metric. Okay, and that goes more broadly than this course. That goes like if you're reading theorems in another book or on Wikipedia or anything. If the theorem is about a normed vector space and it's talking about like continuity or anything to do with a metric, then you should assume that the metric they mean is the metric induced by the norm. Okay, that's the fancy word for this, is that this metric is induced by the norm. Okay, and it's really kind of rare that you find a theorem that's about a normed vector space where the metric is anything else. Okay, are we good so far? So we have metric spaces. Within metric spaces, we have this subset, which are the normed vector spaces. Normed vector spaces always have metrics, so they're always metric spaces, but not all metric spaces are normed vector spaces. Daniel has a point. Two vectors can have the same norm, but not be equal. Yeah, so two distinct points will have.
It's just to show that what I said wouldn't.
I know, but.
Or I did plus, I should have done minus.
Oh, yes. Thank you.
Yeah, that's my mistake.
Now I understand. Yes. Okay. So,
Yeah.
So Daniel's earlier suggestion of another way to induce a metric doesn't work. Okay. Okay. Now, some norms are really nice. Okay, so, in fact, let me back up a step. You know, when we're working in vector space land, the metric that comes from the norm is a really nice metric. Okay, now some norms are nicer than other norms. Okay, now the really nice norms are the ones that come from dot product. Okay, so we're going to define dot product. Now, in the more abstract setting of vector spaces, we use a fancier name. We call it inner product. Okay, but it really is just your dot product. Okay. So let's let V be a vector space over R. So that, again, means our scalars are real numbers. Okay, now we get to use our dot notation for functions yet again. An inner product takes two vectors and returns a real number. And it's denoted by angle brackets. So, angle brackets, dot comma dot, it maps from pairs of vectors into the reals. Okay, and now I'm going to list 4 properties of inner products. Okay. Now, these aren't quite the same, although they're very similar. Okay. The first rule of inner products is, if you take the inner product of x with itself, that is non-negative. Second rule, if that inner product of x with itself is 0, then x was 0. Third rule is symmetry. X inner product y is the same as y inner product x. And then you get a fourth rule. Okay. The fourth rule is linearity. Now, actually, the inner product is called bilinear because the inner product is linear in both variables. But number 3 already says it's symmetric, so we only have to state the linearity for 1. So we have Cx plus y, inner product z. Okay. Now, so actually we're combining 2 rules here. There's another rule that's showing up here, and that's that scalars come out. Okay? Any questions on that one? Shall we, let's see, I think we are doing this backwards in the notes right now. I think the next thing we should do is show that inner products give us norms. Okay? Oh, no, actually, I think literally the next thing we should do is an example. Okay, so we could have the inner product of x and y be the sum of the products of their coordinates. Okay, that's the dot product. Let's look at our vector space of continuous functions from 0, 1 to the reals. Here we could define the inner product to be the integral of the product. Okay. Does this example work if we remove the word continuous?
We need the functions to be integrable for this to work, so continuous guarantees that.
Yes, but actually continuity is doing us one more thing.
We get the product is integrable, right?
We actually proved that the product of integrable functions is integrable. Continuity is giving us that. It's giving us that if the inner product of x with itself, of a function with itself, is 0, then the function was the 0 function. Without continuity, we don't get that. Okay.
Could you sketch an example of how that, like a counterexample?
Yeah, so just take a function that's 0 everywhere, but it's 1 at some point. Its integral is 0. Right?
Right, if it has finitely many non-zero points, then okay, yeah, that makes sense.
So that guy's integral is 0. His inner product with himself is 0. But he's not the 0 function. Okay? Now, you could also do the same exact inner product on the space of polynomials. Okay? And in fact, our Rn inner product is a special case of this guy. You can think about the vectors in Rn as being functions from a finite discrete metric space into the reals, and then this integral is, this inner product is an integral. But anyway. Okay, so that's inner product's the one we know, and a slightly new one. We proved before that we can take a norm and get a metric from it. Well, we can take an inner product and get a norm. So if we have an inner product, we can go inner product to norm to metric. Okay, how would we want to define that norm? How would we get a norm from an inner product? Look at the dot product example. So if we're here, we take a dot product of x with itself. We get the sum of the squares of its coordinates, right? How would we get a norm?
Can square root the inner product of itself.
Yeah, exactly. So the slightly non-trivial thing here is that we're going to take a square root. And I need to finish the statement. This is a norm on B. Okay, so in Rn, we have an inner product. The norm induced by the inner product would be this norm. That norm in Rn is the 2 norm. It's Euclidean distance. Okay? Now, we're a little bit short on time. I'll just show the triangle inequality. Let's work through how that works. Now, we're trying to prove it's a norm, so we want the norm triangle inequality. So what we want to do is we want to look at x plus y. Okay? That is, by definition, and let's square it. Okay, and once we square it, by definition, it is the inner product of x plus y with itself. Okay? Now, we can use linearity and we can use symmetry. And what we'll get is that this is x with itself plus 2x with y plus y with itself. Okay? Right, and this is why we wanted. Okay. Now, what's that?
The square of the norm of x.
Mm-hmm. And the last term is the same. It's the square of the norm of y. What about this middle term? Does that ring any bells to anybody? No? Okay. So you might remember, back at the beginning of the semester, there was actually an exercise on this. For this, we can use the Cauchy-Schwarz inequality. So it tells us that the dot product of x with y is at most 2 times the product of their 2 norms. Sorry, the 2 is just carrying along. It tells us that the dot product of x with y is at most the product of their 2 norms. Okay, I'm not writing the 2, I'm not denoting this by a 2 norm here because it's clear that, I mean, we've just said, I'm sorry, because it's not always the 2 norm. This is just the norm induced by the inner product. Okay, but Cauchy-Schwarz actually holds on that level of generality. But I'm going to have to put in less than or equal to here. So this is Cauchy-Schwarz. Now, we're going to prove that next. So I'm just using it here. But I promise I will prove it next. And then this is just the norm of x plus the norm of y all squared. Okay, we started out with a squared norm. We've got a squared norm. Norm of x plus y is at most the norm of x plus the norm of y. That's the triangle inequality. I promise the other four also hold. Okay. But in that proof, we had to use Cauchy-Schwarz. Okay, so our final result for today, we're going to prove Cauchy-Schwarz in its full generality of just an inner product space. Okay, any questions before we do that? Okay. In that case, is that how you spell Cauchy-Schwarz? I mean, is that how you spell Schwartz? I'll double check and get it right in the lecture notes. Okay, so suppose we've got an inner product on a vector space V. And for all vectors, the square of their inner product is at most the product of their inner products with themselves. Okay. Would that have helped us?